In a distributed system, like the ones based on a microservices architecture, there are three guarantees that can be traded off against each other when it comes to data stores: consistency, availability, and partition tolerance. Consistency, which is different from asset transactions consistency, where it's about maintaining data constraints, means that every read operation will receive the most recent value of a write operation or an error instead. Availability means that every read operation will receive a valid response that is not an error, but without the guarantee that it contains the value of the latest write operation. And finally, partition tolerance means that a system will continue to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. With that being said, the CAP theorem, also called the Brewer's theorem, states that only 2 out of these 3 guarantees can be maintained when a system is in a failure mode. As indeed, no distributed system is safe from network failures, and network partitioning must be tolerated, as for when it happens, it must be decided whether to ensure consistency or availability. I'm Raz, and you're watching Explain It to a Duck. Before diving into the details of the CAP theorem, I'd like to introduce you to 2 scaling patterns called read replication and sharding that will help us probe the ideas behind this theorem, as indeed replication is one of the core mechanisms of any distributed system. One way of scaling a service for reads is to use what we call read replicas. A good example would be the one of a service that's responsible for managing the list of products of an online shop. In that context, it is quite safe to say that the database containing these records is usually under more stress on reads than on writes, as customers will access the products list more often than developers will update it. When using this pattern in combination with a relational database management system, all writes are directed to the primary database node that will in turn copy the data to one or more replicas in order to allow for future reads to be distributed. Although this technique is great to ensure that data is kept safe and that the main node doesn't have to cope with so much querying stress, it may sometimes happen that the service responds with stale data until the replication has completed. Such configuration is then designated as eventually consistent. Despite the fact that it's a fairly simple and common way to help scale a system, I would rather suggest you look first into caching, as it can often deliver a much more significant improvement in terms of performance with less implementation efforts. If you'd like to know more about caching techniques and relational databases, I invite you to watch the 2 videos I made on these topics. I'll drop a link in the description. Now that we've seen an easy scaling pattern for reads, let's discover another one for writes called sharding. In short, sharding is the process of splitting either horizontally or vertically a primary database into multiple databases nodes called shards. In horizontal sharding, the tables of the primary database are duplicated and the data is broken up and spread across the different copies, which means that tables will have the same attributes but distinct records. In vertical sharding, which is by far more complex, the attributes of the tables are divided into smaller tables where the data is broken up by attribute, which means that tables will have both different attributes and records. The benefit of this approach is that it greatly decreases the response delay as well as providing an increased resilience to failure, as indeed executing a simple request on sharded data will be more efficient, as the search will only be performed on a subset of records, and since shards are more likely to be located on different machines, the impact on the system of a server becoming unavailable is mitigated. But the flip side is that the complexity automatically increases when handling queries that requires data joins, like for example trying to find all of the customers over 18 years old. The addition of extra shards can prove challenging without the right database management system, as there might be a need to take down the whole database in order to rebalance data. And finally, the resiliency might not be actually improved if one or more shards are unavailable due to the lack of data replication. Scaling for writes is therefore tricky and really requires to explore the various capabilities of the different databases available on the market. Now that we have a better idea on how a distributed database system works, Let's have a look at the challenges associated to it pointed out by the CAP Theorem. Let's take the example of a service that uses the multi-master replication pattern in which two master databases are directly connected through a network link in order to synchronize data between them every time a new write operation is performed. When everything goes well, both consistency and availability can be achieved due to the two-way replication process. Imagine now that the link between these two nodes somehow fails and the replication becomes impossible for a certain period of time. Of course, modern systems usually include a queuing mechanism to avoid message loss and to ensure that the service can recover at some point, but what happens in the meantime? Well, it turns out that when this happens, we have to make a choice between consistency and availability. Sacrificing consistency means that we decide to let our service process incoming requests, keeping it therefore available despite the network partitioning while taking the risk of serving potentially stale data, which in turn implies that the longer the partition lasts while accepting writes, the more difficult resync will become, and such a system is designated as an AP system. On the other hand, sacrificing availability means that to keep consistency, each database node must be able to know that the copy of the data it owns is the same as in the other nodes. In the context of a partition, when nodes are unable to coordinate, the only option is then to refuse to respond to the request by sending an error message instead. And such a system is designated as a CP system. Now that I've presented to you the two possible system trade-offs, the question remains, which one is best? And the simple answer is, it depends on the business impact it will have. Imagine that you are developing a PHP app where the customers can track in real time the chauffeur's position and the ETA to the pickup spot. Would it cost for your customers to cancel their ride if your chauffeur's real-time location was out of date by a few hundred meters, or if the ETA to the pickup spot was wrong by a couple of minutes? If the answer is no, then trading consistency for availability might be the right answer, as customers would rather have approximate information rather than no information at all. Imagine now that a chauffeur accepted the ride and is driving towards the pickup spot. Would it be a problem if the pickup address was the last known address from a previous ride and not the actual one the customer is waiting at? If the answer is yes, then trading availability for consistency might be the right answer, as sending the driver to the wrong address would cause for the customer to cancel the ride and the driver not to trust your platform. And that wraps it up for today, guys. Thanks for watching. Feel free to share, like, and comment this video if you find this content useful, and see you in a week for another episode of Explain It to a Duck. Cheers.